Hi, my name is Monica Gracida, and we will be streaming right now about valence electrons and ionic compounds. Can everybody hear me and see me properly? Excellent. Let's start. Okay, so this stream, don't forget to follow us through social media at Thinkable. Okay, this stream is going to be about, we're going to cover electron configuration for transition metals, valence electrons, placement of the elements on the periodic table, and basic bond formation. Okay, just a reminder, remember last video we covered how to do electron configurations using our Gauss chart and using the periodic table. And since in the AP exam and always in chemistry we have availability to a periodic table, it's easier to do it using the periodic table. So if you remember, using the periodic table, we just follow the order of the elements, right? And we go 1s2, 2s2, and we follow along. I'm showing here in the mouse. 2p6, and it's the same order as in our Gauss chart, the order of energy. Then 3s2, 3p6, 4s2, and do we remember what happens on this level, on the transition elements? Correct. What happens here, Natalie, good, is that after 4s2, we need to go back to a third energy level to fill up the 3d10 level, and then 4p6, we follow along the periodic table, 5s2, 4d10, 5p6, and here 6s2, and then we follow the numbering of the periodic table. So we go from 6s2, sorry, to 4f14. Once we're done with these elements, we go back to 5d10, 6p6, 7s2, 5f14, 6d10, and 7p6. Just a quick review or recap of last video. Okay, with this in mind, let's start doing electron configuration for the transition metals. Transition metals are slightly different than the representative elements. Okay, so scandium has an atomic number of 21. Do we know that what 21 number means? 21 what? Number of protons, correct. And if we're talking about an atom, that means that it's a neutral atom, so the number of electrons should be the same. So we're going to do the electron configuration for 21 electrons. And let's remember the location of scandium, which is right here, the first transition element. So what would be the electron configuration for scandium with 21 electrons if we follow along the periodic table? Remember, the location is right here. We follow along and it would start with 1s2, 2s2, and then correct, Luca, very good. You did the abbreviated electron configuration, which is correct. Excellent, Camila, very good. So when we do the electron configuration following along the periodic table, we end up having this electron configuration. The abbreviated as Luca already gave us the answer, is when we place brackets and the noble gas before that element, and then the configuration that follows. Very good. Okay, now I am going to take a moment and do Bohr's diagram step by step so that we know what would be the basic difference in transition elements. So Bohr's diagram, if we remember, it's a diagram in which we place the elements in energy levels. So we start with scandium, 21 protons in the nucleus. The first shell will have 2 electrons. Right? The second shell, how many electrons? Remember, that is the whole shell. So we're going to add the superscript that represent the electrons. So the second shell will have how many electrons? Correct. Correct, Luca. 8 electrons. Correct. Paula, very good. So the second shell will have 8 valence electrons. Then if we do Bohr's diagram in the order of the electron configuration, then we will open a third shell with also 8 valence electrons. And here is the difference in transition elements. We have to open a fourth shell with 2 electrons. And then the last electron that we're going to place is going to go in an inner level, in the inner third level. So right now on the third level, we have the 8 electrons that we have before, plus the last electron. So we will end up with this electron configuration, with this Bohr diagram, sorry. So we are here for scandium. And this is something that happens in all the transitions. And the reason is that if we remember from our Gauss chart that organizes the energy sublevels by energy, it will be less energy to open a 4s than to open a 3d. So that's why we have to open a fourth shell first before filling up more electrons on the third shell. And this happens with all transition elements. Any questions so far? Okay, we are going to continue. So now we are going to do the electron configuration of the next. Correct, Dylan, very good. Yes, the third energy level will hold a total of 18 valence electrons, correct. So now that you asked this question, what would be the total electrons that the fourth shell could hold? We add all these subscripts. And how many electrons can the fourth shell hold? Okay, so the answer is 32 electrons on the fourth shell, 18 on the third one, 32 on the fourth one, 32 again on the fifth one, 18 again on the sixth one, and 8 on the seventh shell. Okay, let's move on. So if we do the electron configuration abbreviated in Bohr's diagram for the next transition element, which location would be right here, this is what we will get. And again, the last 2 electrons from the electron configuration would be on the third shell. If we do the same with the next transition element, we follow the same pattern. And we go on, and the last electrons are on an inner third shell. Okay, in chromium, something interesting happens. If we follow the rule, our Gauss rule, and the periodic table, we will end up with chromium with this expected electron configuration. But with experimental data, we notice that that's not the real thing. The real thing, the real one, looks something like this, where the third D shell has 5 electrons and the fourth one only has 1. Correct, Paula, that's an exception. Excellent. So the reason for this exception, as Paula is saying, is because this is the expected orbital diagram where you have a fourth S level, sublevel full, and an incomplete 3D. And the observed is that the third D will be better, will be more stable if it's half full, and the 4S will be half full as well. So this is observed. This is what chromium does because this is more stable for chromium. Just a quick note here. You won't be asked to memorize the exceptions for the AP exam, but maybe you will be asked to explain why the observable is different than the expected. And the reason has to do with the stability of the d orbitals. Any questions so far? Exactly. So our bow exceptions have to do with the stability. Okay, let's move on. If we do so, again, the Bohr diagram for chromium, considering this stability, it would be only one electron on the fourth shell, and the last, the 5 electrons that come last will be added to the third shell. Okay, manganese, which the location is here, we will follow the same pattern, placing the last ones on the third shell. Iron, location here, and this is its data. Cobalt, location in here, so we will have 7 3D electrons. Nickel, location here. And then again, we have an exception for copper. This is what we would expect. What do you think would be the observable configuration? If this is the expect one and on the same trend of the stability, what do you think would the change be? What do you think the real? Exactly, Camila, very good. The real one, as Camila is telling us on the chat, is 4s1 3d10. And the reason is the same as before, stability. The expected is the one above, where the 3D is incomplete. So the 3D is more stable since it needs more energy. It's more stable if it's full, and then the 4s can be half full, and that's totally fine since this one needs less energy for the electron to be there. So in both cases, it's always, the answer will always be stability of the 3D orbitals, in which either half full or completely full are more stable than intermediate levels. Excellent. So we are in copper, and the last transition of the row. I'm sorry. So on copper, as before, we will have only one valence electron on the fourth shell, and 3d10 on the third shell, completing the third shell with 18. Now we have the third shell full with 18 electrons, with one valence electron in the fourth shell. So zinc, location here, we will have this data. Now the third shell again will be complete, and the fourth shell now has its 2 valence electrons. Any questions so far? Okay, we are going to move on. What do you think we have to do if we need the configuration of the zinc ion? The zinc ion has a charge of 2+. Are the elements in the exceptions more reactive? Okay, Camila, not necessarily more reactive, Well, they will lose, for example, copper. It can lose. Remember that some of the transition elements have several charges. That is due to the fact that the transition elements are able to lose the outer shell and some of the inner shell. Because remember that the ions look to be stable as noble gases, and that would mean to complete the octet. Since there's no octet if you remove this one, that's why transition elements can remove this electron, the outermost, and some of the inner one. So not necessarily more reactive, just different instability. Okay, so we were on the process of doing the electron configuration for the zinc ion. The zinc ion, in fact, this is a transition element that only has one charge. The zinc ion has a charge of 2+. What do we have to do the electron configuration of the zinc ion? How many electrons should we consider? If the zinc, correct, Camila, 28 electrons, since protons are 30 and those we cannot change them, we do change the electrons. So to be able to reach a charge of 2+, yes, we will do 28 electrons. So if we do the same with 28 electrons, these 2 electrons that are being lost on the ion are the ones on the 4th shell. So the 4th shell would be lost to other ion, to a negative ion that will accept it. And this would be the electron configuration for the zinc ion, with the 3rd shell complete with 18 electrons and the 2+ charge because of the difference of the 30 protons and the 28 electrons. Okay, let's move on. So just a recap of the groups on the periodic table. As you can remember, there are 2 numbering systems on the periodic table, one that goes with the numbers 1 through 18, and another one that uses labels of A and B. The A is used for the representative elements, and B is used for the transition elements, which are the ones in the middle, and also these ones. These ones are called inner transitions. Okay, the representatives, they're called representatives because it's very easy to predict their behavior. Since they don't feel inner levels for the electrons, like the transitions, it's very easy to predict what ions will they form. So with this in mind, how many valence electrons do you think there would be for the first group, for 1A group? Remember that valence electrons are the ones located on the outermost shell. So how many valence electrons on group 1A? Yes, correct. 1 valence electron. What about in the group 2A? Exactly, 2. And then let's keep the transitions for now, and let's go to the 3rd level. How many on the 3rd A level? 3, correct? Correct, 3. And if we move to the 4th one? So we can see a pattern now. Correct, Paula. So it would be 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Correct. What about the transition? How many valence electrons will the transition have? Remember, valence electrons are the ones on the outermost shell. So how many valence electrons on the transition elements? Excellent, Luca. Yes, 2. Remember that you open remember Scandium? You open the fourth shell with 4s2 before placing inner electrons on inner levels. So yes, the valence electrons will regularly have 2 valence electrons. Of course, there are exceptions, like in chromium, in which you will have 1. So there's some exceptions, but in general, the valence electrons of the transitions, as well as the inner transitions, are 2. Another exception is helium, which is a noble gas, but contains only 2 valence electrons because it is stable with only the first shell full. Any questions so far? Okay, now that we have the valence electrons, what do you think the charge of the ions would be? What would be the charge of group 1A if it forms an ion? Remember that ions are atoms with a charge. Correct. Correct, Sonia and Nicole. Correct. +1 for group 1A. And let's go with the trend again. What about the second group? Excellent. The second group will have 2+. What about the transitions? What charge will they normally have? Yes, Luca, 2+, or it could have different charges because remember that it can lose those 2 valence electrons and some of the inner electrons as well. Okay, what about group 3A? What would be the charge for this group? 3+, correct. What about the next one? Very good. 4+ or 4 negative. Why? Why both of them or either of them? Remember that the purpose of creating ions, excellent, Camila, because it's the energy needed to gain or to lose for is the same. Correct. Excellent. All of these answers are correct. It can be stable both ways. It takes the same amount of energy to gain or to remove for. Remember that the purpose or we're aiming for to be as noble gases that have 8 on their outer shell. Excellent observation, Dylan. Correct. For example, carbon is located here, and it will usually make covalent bonds, sharing its electrons instead of losing or gaining. Excellent. Covalent bonds are formed easier with groups with carbon and silicon that are elements of the 4A group. What about group 5A? What would be the most probable charge of the ion? Excellent. 3 negative, because remember, they want to be as the noble gases, so it would be easier to gain 3 to complete the octet than to lose 2. So we have the pattern already, right? What would be the charge for this one? For groups. Excellent. 2 negative, and then the charge for 7A. 1 negative, correct. Lastly, the noble gases, what charge do they have? 0. Excellent, Nicole. Yes, this is correct. So those are the charges of the ions. If the atom will lose or gain electrons to turn into the ion, That is the thing that most likely they would do. And again, a recap of the representative elements. This is because we can predict very easily its charge. So we can predict very easily how would they behave chemically. Questions so far? Okay, we're going to move on. So another way to, well, the most common way to classify the elements in the periodic table is by classifying by metals, nonmetals, and metalloids. But it always refers back to the valence electrons. So the metals would be here there in pink, and they're metals because they're most likely to, what do you think metals will most likely do? Lose or gain electrons? Excellent. They will most likely lose electrons and they will gain a positive charge. What about the nonmetals? Will they lose or gain electrons, the nonmetals? Correct. Gain electrons, and we can see here that hydrogen is considered a nonmetal, even though hydrogen can act both as a, can lose one electron or share one electron. And then we have the metalloids here displayed in green. These ones will have characteristics of both metals and nonmetals. Okay, we're going to move on to the basic bond formation, which is pretty simple. So we know that ionic bonds are formed by transferring electrons. The atom that usually loses the electron is called the cation, and most likely it will be a metal. And the atom that gains will be called the anion, usually a nonmetal. A good easy way that I remember which is the positive and which is the negative is by the T of the cation, a positive sign. So that's the positive one. I hope this is useful. Let's do an example. For example, sodium chloride. How is this ionic compound formed? If we remember its electron configuration, I have here both electron configurations and both Bohr diagrams. We notice that sodium has 1 valence electron and chlorine has 7. So what would sodium do? Correct. It will lose this 1 electron because if it loses this complete outer shell, and then it will fulfill the octet. The second shell will have 8. So it will lose its valence electron to chlorine, and now chlorine will have 8 valence electrons on that 4th shell. So this electron gets transferred. By transferring that electron, the electron configuration changes because remember the electron configuration of ions, you need to consider the electron that was lost and the electron that was gained in here. And notice that both outer shells now have 8 valence electrons each, so they're more stable. And they're kept together by attraction because they have opposite charges. Now sodium will have the sodium ion will have a smaller radius. And I made a mistake here on the slide. I'm going to correct it later. The chlorine ion will have a larger radius than the chlorine atom because it is completing its outer shell. And also because you have unequal amount of protons to electrons. You have 1 electron more than the proton, so the nuclear charge is not able to hold it close enough. So the sodium ion will be smaller than the original atom, and the chlorine ion will be larger than the original atom. but they will reach more stability because their electron configurations are going to be as the ones in noble gases, as neon and as argon. And that's why they're kept together with this attraction. So one thing to consider for ionic compounds is that the formula unit of sodium chloride, it's only telling us the ratio in which sodium to chloride bonds, but it actually forms a crystal lattice where you can have millions of sodium to millions of chlorides. And the unit 1-to-1 forms a distinct crystal lattice. In this case, it's a cubic shape because the ratio is 1-to-1. Let's do another example. What do you think will happen to magnesium with 2 valence electrons and bromine with 7? What will happen in this case? What would magnesium do? Correct. The ratio would be 1-to-2. Correct. Excellent. You will need 2 bromides, correct? Because magnesium will lose the 2 valence electrons that it has. Correct. One to this bromide and another one to another bromide. Remember that the formula unit is just the ratio, but you have millions and millions of atoms combining or having like this relationship to each other. So transfer of 2 electrons for magnesium, gaining a 2+ charge. The bromides are accepting these electrons, gaining a negative charge. So one thing to consider is that they will be very distinct crystal lattices, and this depends on the ratio in which they will combine. For example, salt will have a cubic form, but if the ratio is different, we will have a different crystal lattice. And we can see the beautiful crystals. When we have ionic crystals, they form different of these crystals depending on the ratio in which the ions combine. Questions so far? Okay, let's move on with covalent bonds. In covalent bonds, we know that they're formed when the atoms share electrons. This usually happens between nonmetals. For example, something very simple, it's with 2 fluorine atoms. If we notice here, the fluorine atoms have 7 valence electrons. They only need 1 to complete the octet. So by sharing the electron, one thing to consider is that the shared electrons count for both atoms. So now both atoms are complete with the octet, and they will be the electron configuration just like neon, so they're more stable that way. Okay. Fluorine, F2, is a set of elements that are called diatomic elements. Diatomic elements are the ones that in nature, they always exist combined in pairs. And this is the reason they're more stable together than separate. These are also called the magic 7. Do we remember which ones are these diatomic elements? Which are these 7 elements that form diatomic compounds? Excellent. Those are all great answers. The magic 7, yes, they're located in group 7, the majority of them. Nicole, very good. Hydrogen is also considered. Oxygen, nitrogen. Excellent. So these are the diatomic elements, hydrogen, and this one's right here. They're called the magic 7 because the location in the periodic table kind of look like the number 7, and they're actually 7 in numbers. So these ones bond covalently, again, because they're more stable in pairs than on their own. So hydrogen will end up having one single bond with one pair of electrons shared. Nitrogen will form a triple bond because it shares 3 pairs of electrons. And oxygen forms a double bond because it shares 2 electrons. Okay, the lines, there's 2 ways to show Lewis structures for compounds, with the dots representing the valence electrons, and also lines to represent the shared pair. So these lines are the same as this one. And the ones that are not being bonded, like here of nitrogen, these ones, do we know how these ones are called? These ones are the shared electrons. What about these ones? The ones on this side of nitrogen. Do we remember how they are called? Excellent, Sonia, correct. These are called the lone pairs. The unshared electrons are also called the lone pairs. So we can see here that in the oxygen molecule, we have a double bond, and each oxygen atom ends up having 2 lone pairs. Excellent. Okay, and yes, as Luca mentioned, some of the elements of group 7A will also be part of the diatomic elements, and they will all form single bonds. Questions? Okay, we're going to move on. Besides the diatomic elements, we also have other examples. For example, water, it forms this covalent bond oxygen with hydrogen. And now you can notice that oxygen completes the octet, 8 valence electron. And hydrogen only completes 2, which is totally fine because the first energy level has a maximum of 2 electrons. So hydrogen, when it shares, it resembles helium. And here we have carbon dioxide, in which every carbon and oxygen atom share 4 electrons, right? So we have 2 pairs here of electrons being shared, and then here we have another. So carbon dioxide bonds covalently with a double bond, and each oxygen atom still has a pair, 2 pairs of lone pairs. Questions so far? Is it clear the difference between ionic and covalent bonds? Okay, something that I want to mention here, another part of another review, is that the formula of covalent compounds, like a carbon dioxide molecule, is actually 1 atom of carbon with 2 atoms of oxygen, versus the ionic, in which it was the ratio. Remember the ratio of the crystal lattice? So that's a very important difference between covalent and ionic bonds. Ionic bonds, the formula, it's a ratio, and it could be millions and millions of ions in the sample. And in here, we have just 1 atom of carbon per 2 atoms of oxygen existing on the carbon dioxide molecule. Yes, Camila, very good. You remember from the last video when we did the empirical formulas. Empirical formulas only, I'm glad that you mentioned it, because empirical formulas only make sense for covalent bonds, since they can have a lowest ratio. in covalent bonds. But in ionic, it doesn't make sense because the formula unit, it's already the smallest ratio of the formula. Excellent. Great job. Excellent. Any questions? Okay. From my part, that's all. I hope this video was useful. Thank you for your attention, and see you next time. Okay? Thank you, Alex. Yes, he's commenting that nice drawings, and yes, I made this myself with a whiteboard, so I hope you like it. Thank you, Isaac. Thank you, Santiago, Gloria. Thank you. See you next time. Bye. Bye, Dylan.